Welcome everyone. Today is September 14th, and this is another of our bi-weekly batch work group meeting. My name is Mati, and I'll be your host today. And we have Francesco and Adam with us as well. So let's start with Francesco and his Numa Hour scheduling update.
Hello, everyone. So I'm trying to share my screen. This is new. I'm trying to share. Okay, share. And now hopefully you see the presentation.
Yes, we can see your presentation.
Okay, thank you very much. So I'm going to, too early. I'm going to talk about the Numa scheduling effort. How is it going? What are the updates are since the last time we spoke about. For people which, for folks which attended the KubeCon Europe presentation, some of things will be not new for you, but I'll try my best to not duplicate information. So without further ado, what we are covering today is what we managed to accomplish up until last time, what we believe, actually I take responsibility, what I believe is most important for this forum, and what we are planning and what's already in motion for the future. Just a very quick recap for folks which are maybe not completely familiar with this initiative. Basically, we started from an issue in Kubernetes, which is about what happens if the node is configured with the topology manager and strict alignment, because you can require strict alignment on kubelet, and the workload is rejected because the kubelet cannot fulfill the guarantees required in the pod spec. You get topology affinity error, you get few unpleasant circumstances because the controller, for example, random example, a replica set controller cannot really deal with the error and keeps it creating pods and pods and pods. So one way, which is the way we're talking about to solve this, is make the scheduler more aware of those the NUMA nodes, and to make so, it turns out we need quite a bit, some bits and pieces, namely a new scheduler plugin, which needs new data to work with, which is expressed by this API called Node Resource Topology. And we need some agents which provide this data, much like the kubelet will provide the node data. So you have much more details in the KubeCon Europe presentation, which I'm referring to, and this is basically it. This is what we are working with. So what we managed to accomplish. Okay, the good news is it's there, is pretty much feature complete, and for what we see, it's working. So we are entering the hopefully boring phase, on which it's about bug fixing, it's about keeping up with kubelet changes, and to make sure the scheduler side is fully aligned as much as it could be with the kubelet side. It's about performance optimization. And I think this is one of the instances on which boring is good. So we are now looking forward to integrate, for example, one test suite we built, because I'm with Red Hat, and Red Hat is actually looking at that and supporting that. So along the way, we built a test suite, which we are looking, for example, options to merge, for example, with scheduler plugin. To some extent, it's an ongoing conversation. I just want to mention that there are non-trivial challenges, because to properly exercise this side, you actually need multi-NUMA machines, which are pretty hard to find in the cloud. So what I'm trying to say is that there are maybe non-trivial challenges which are looking about how to explore. And one thing which I just want to mention quickly, because it's the first bullet point, is that we actually managed to complete the caching side, which was important to deal with the misalignment, the propagation delay between information reported by nodes about the resource allocation and the scheduling view of that. So we need a caching support to overcome the the performance side of things and to have a good scheduling decision. I'm going to talk again about a bit more detail about this problem and why it's relevant later. But and if people are curious, want to get in touch and understand the full extent of it, we can just chat in the usual channels. So since I mentioned we are entering the hopefully boring is good part, we are more and more focusing. Okay, let's make sure people which are interested they have as much as easy possible way to try it out. So we are still continue investing about making easier to consume. For example, we have a project which is a tool and a set of packages to make it trivial to deploy this project. We talked about this is not seen an alternative of Helm charts, but because we needed to integrate a bit of missing parts, we basically need a bit of more logic, and we built an operator on top of that, which we didn't want necessarily to see as the main way, because we wanted to give freedom to people which just want a manifest, for example. So we built this tool and this set of packages to make it easy to consume. And we also have a quick start environment on Minikube. Why Minikube? With respect, for example, to kind, because this way you can mimic multi-NUMA architecture, which is, again, a challenging side. Getting a multi-NUMA machine on the cloud is, it's not the hardest thing in the world, but it's not trivial either. So Minikube could help in that regard, because it could, being a virtual machine-based solution, could actually fake those multi-NUMA environments. And I have a couple of demos, but I will just like to, for the sake of time, I will just to postpone it at the end, and then I will ask the kind moderator if we have enough time, and we'll see a couple of demos. There is one demo which explains the achievements with respect to the cache side I mentioned about scheduling decision, and we have another quick demo about the deployer thingy to make easy to consume this stack. So let's just postpone that at the end of the session, depending on time and questions. So highlights, things that I believe are interesting for this forum, which we discovered or had to face during development of this project. So some of them are, I believe, novelty factors and challenges. So let's see some of them. So I mentioned this cache thingy. Why do we need a cache thingy? Why do we need a new way to synchronize the state between the scheduler plugin and the node side? Is because the design of the kubelet and the implementation of the kubelet with respect to resource allocation, which is the one piece in the cluster, in the stack, which decides which how do we actually allocate resources. Okay, I am a pod, I want some CPUs, I want some memory, I want some devices, I want them on a given NUMA node, which the component which decides the final location runs on the kubelet, and the scheduler cannot drive that behavior. Basically, you have to guess and hope. Okay, this is a bit, brutal explanation, but that's actually not far from truth. The scheduler says, okay, I think this node has a quite high chance to fulfill this requirement, and our efforts are about to making this prediction as good as possible, but ultimately you don't know what happens on the node up until you actually hit the node, and you don't know where resources are located up until the allocation takes place. An easy example is that with the node resource fit plugin, you can say, hey, I'm sending this pod to this node, so I know for a fact that the resources is going to be decremented, the CPU availability is going to be decremented. With NUMA in the picture, you say, okay, on some NUMA node, the resources is going to be taken. I cannot predict which NUMA node is going to be. I need to wait to learn which NUMA node is going to actually be taken, from which NUMA node the resources are actually taken. Why? Because the allocation is on the node, and in the current architecture, there is no way to do it differently. The SIG-node community is exploring new ways to improve that, but for now and for the known future, that's it. So the scheduler needs to know, to deal with this uncertainty. The node does the information we cannot predict, we can only learn after the fact. And this is, to the best of my knowledge, something that's not very common in the scheduling area. And this is another challenge or novelty factor we faced, which is probably more unique to this initiative, which is along the way, with the help of other community members, we created this CRD API to represent the NUMA architecture, because you need to account the resources not just at node level, but at NUMA level granularity. So how do you represent the actual topology? Because it's very hard to actually have a canonical representation of the hardware topology, because it's getting very complex very fast. So we need the flexibility. But with great powers come responsibility, because now there is no longer a single canonical representation of the topology of the node. There are multiple different and legal representations. So how to ensure the best compatibility within how the producer on the node represents the information and how the consumer side is consuming them. We have some solution. We have some ideas we are exploring to make it better. But the key point is that there is a significant component of acknowledging the fact that the very resource which we want to represent is complex and hard to predict, and one size is hardly fitting all. So this is, again, more than an incidental complexity and acknowledgement of what we are trying to do and how complex is the scenario. And this is probably very specific to what we are dealing with, is that this is actually an issue which was very interesting in we hit it not so long ago, which was about the fact that the kubelet reports the resource allocation also for pod in terminal phase, because up until the pod is actually gone for good, you cannot really reallocate resources. On the other side, the scheduler deep inside does a filtering to not get from the API server the pod in terminal phase. So this is probably the most specific and less general issue we've seen so far, but I think it's worth is still worth mentioning. And the slide, yes, the slide is has some stale data, which I will fix later. Now, operating and debugging the scheduling side. So presented another set of challenges, which I'm going to just to touch very quickly, which is one of the very goals of this effort is, okay, having a good scheduling decision, and in the context of NUMA aware scheduling, where things are more complicated, because when NUMA is in the picture, we see the users of the feature cares quite a lot about, okay, how the actual allocation is done. This means that quite often we had to get into the details. Okay, we decided to go in this node, and this node we did this allocation because X, Y, Z. This is not exactly what we wanted. So there is a degree and interest in learning the fine details of annotation, which from our experience was a bit more than we were used. And actually getting into the internal scheduler state was challenging. It's actually still an open question, because exploring and being able to explain why a certain decision was made is proving to be quite challenging, and people cares about those details. So operating, what we found lacking, or we are trying to improve, is that one thing which again, those things are probably more for SIG instruments, but it's still something which we faced while operating, is that we would really like to have logging more dynamic, because, okay, we can just restart the scheduler, for example, or any other component and increase the verbosity. No big deal. Problem is you lose the runtime state. And sometimes getting to that runtime state takes a while, or it's challenging. So being able to change it dynamically is something it would actually help us and ease some of our pains. And and this is an open challenge, probably not the best form, I still wanted to mention it. And another thing which will help us operating the scheduler, and probably other solution, is that getting a peak of the internal state somehow, not necessarily attaching a debugger to the live debugger or picking the endpoint is could be important. Why? Because sometimes you learn only after the fact. So it's not just, we cannot just always debug it live. Sometimes we can, sometimes we cannot. So having a way to pick on the state would be helpful. How? Open question, but still it's something we faced. Finally, last challenge is that we had in the current implementation to second guess to a large extent the topology manager on the node, because we cannot disable the node to get the NUM alignment. So we have this, two brains in a body, in a cluster, and because we cannot just drive the decision from the scheduler side, like, okay, dear node, I am choosing you, and you're gonna allocate this way in this node, in this NUMA node, like I'm telling you. We cannot do that. So we cannot move the logic on the scheduler side yet. We cannot disable the logic on the node side yet, or probably never in this architecture. So we need to have those two entities cooperating. At this point in time, we have a simplified version of the allocation logic, topology manager allocation logic in the shader plugin. It will be nice to be able to use the same core algorithm and possibly the same code itself. Doing that is a matter of refactoring and some redesign, and that's actually the challenge. So we are trying to see if and how we can make it happen. Now, what lies ahead? Again, nothing, groundbreaking. We really want to polish the API and take the chance before to go to beta 1 to fix things and clean up things and stabilize, bug fix, make it fast as possible, make it consume less resources as possible, and in the near future, possibly next cycle, no promises, but maybe starting cycle 130, starting to move to see if and how we can merge this if there is interest and possibility, we like so to merge it in Kubernetes itself, to have it in the core. Start this conversation. So references. Thank you, folks. Any questions? If we have time, I would be happy to do the demo. So that's it.
Maybe let's start with questions.
Sure.
Do we
Sure.
have folks with any particular questions? With regards to the dynamic logging, there's a long-standing issue that I linked in the chat because I remember very early on, I just looked at the issues from 2017. People were asking. I was recently talking with our SRE team, which was similarly asking about the ability to debug a problem without the requirement to restart, because usually when there is a problem at hand and you do restart, the problem disappears for however long it takes it to reappear. I don't see. Does anyone have any questions? Last chance.
Yes, there was a slide about pod in terminal phase. Like this. Can you explain a little bit more what was the issue there?
Yes. So it will take a few minutes, but I'm trying to give you the picture. So basically, because we need to wait. Okay, let me start from the beginning. The NUMAware shadowing, the NUMAware shadower plugin does its own accounting of resources with NUMA level granularity. Based on that, it says, okay, I really believe that this pod could be accepted and aligned correctly by this given node A, say. Okay. It sets spec node name to node A, and then the node A comes, the kubelet picks it up, actually aligns it, and fine. You can you get the resources allocation, but the shader plugin cannot say, okay, I think it's gonna be on node 0, on NUMA node 0, NUMA node 1. You cannot predict it. You can only learn after the pod is admitted. So you need to wait for the state to get back to the state to be updated from the node agent on that node. You watch this update, and you update your state internally. To make that solution resilient, the thing is that you need to make sure that the state you update is the state you expect. Okay, I'm expecting an update after this pod landed. So how do we actually recognize that this state is matching my expectation? To do that, we list all the pods which are expected on the node and the one which are actually running on the node, and we know that on the scheduler side, watching the pods from the API server, and on the kubelet side, listing on the pods which are reported by the pod resources API. And we compute like an hash, and when and we attach this hash to the update, it's an annotation, like for example, and when those match, the scheduler said, okay, I can trust this update. This match the state I'm expecting, so I can update. This is the simplified, but not much simplified. To compute this, the expected state, you need to enumerate all the pods. To enumerate all the pods, the kubelet reports the pod in terminal phase. The scheduler is not, because the scheduler actually, the scheduler framework does filters out when it's open the subscription to the scheduler, filters out the pod in terminal phase. So we have this mismatch. Could it just be a kubelet bug? We are discussing that. So, but this is the story.
Do you have maybe a link to an issue?
Yes. Yeah, I will share in the agenda. Again, I'm not saying this is, this is possibly the most, implementation specific thingy, but still works. It was painful to discover, yeah. But yeah, I will share in the agenda just after the meeting.
Yeah, that would be great, because I believe one of the reason Michal was asking this question is when he was working on the job conditions, especially the ability to configure how we are treating various closing, finishing statuses of pods within a job, how to treat them, allow users to configure them. He was struggling with several different issues around terminating pods. I remember reviewing at least a couple of PRs around the topic, so I'm pretty sure that he's just curious about various approaches, and that could probably be useful to both of you to know cross-reference.
Absolutely.
Thank you.
Yeah, exactly. So that was my motivation. So yeah, if you could, I'm not sure I fully followed in this case, but yeah, in 127 there was like pretty significant change how kubelet reports terminated pods. So
Yes.
before there was no guarantee that pod would enter the terminal phase, and this was causing problems for job.
Yes.
Okay. Do we have any other questions for Francesco? Okay, hearing none. I think we have like 18 minutes left. Adam, before we switch over to you, how much time do you need for your topic? Is 15 minutes enough for you?
Yeah, definitely. It won't take me too long.
Okay. So for those interested in the demos that Francesco had in his presentation, the presentation is already linked in the agenda. So all the folks interested in having to see the demos, I'll ask to just follow the links from the presentation, and we'll move to Adam. And if there will be some time towards the end, we might return to Francesco, but I would prefer we give Adam sufficient time to cover his topic. You should be able, Adam, to share your screen, so just go ahead.
Thank you, folks.
Thank you, Francesco.
Yeah, hey everyone. So basically what the reasoning for creating this document was Kubernetes uses the word scheduling for something very specific, which is pods being scheduled by Kubescheduler, and kind of everything else doesn't nicely fit into the word scheduling, which is a very different idiom to how high performance computing would look at it, where everything would be scheduling and there's only one type of resource you really schedule in the world. So this document is an attempt to create a language that we can use within the Kubernetes world to correctly understand the differences between all the different kind of scheduling methods. And the reason I think this needs to exist is depending on what you've done with your scheduling solution, it makes it very different what can be possible with it and what parts of Kubernetes you're touching and what kind of issues you're going to face. So that's kind of what this is about. And to make it very clear what I'm trying to get into this document, it's not about what the user necessarily submits. It's more about trying to find a language to describe what bits of Kubernetes it's touching. And that kind of tells you what kind of control loops you're entering. So this is very much a draft to begin with, so I'm sure the language of this is going to change. Feel free to leave comments in this and we can work on it over time. So to try and get around that I can't use the word scheduling, I've come up with a new term to describe this idea of all the different types of scheduling. So I've called it batching. So this includes scheduling, queuing, and dispatching, which are all terms that have been used to describe this kind of thing in Kubernetes. I've got a batching object, which is basically the things that can be controlled with these higher level batching softwares, so CRDs, jobs, and pods. And the batch interfaces are the control loops that you could enter. So for example, you could enter directly to the scheduler, directly to the Kube API, or using the suspending / gating system. So it's suspend field for jobs and it's the gating field for pods. And in general, I think by using that language, there's 3 general questions you can ask about any solution for batching on Kubernetes. So you can ask what's being batched. Is it pods? Is it jobs? Is it CRDs? You can ask where is it being batched? So single cluster and multi-cluster are kind of the easy ones there, but I've tried to get some idea of out of cluster and inside other batch objects. And what I mean by that is out of cluster, an example would be Armada, because Armada's scheduling system doesn't have to live inside Kubernetes. It just controls objects within clusters. And inside other objects, an example would be the flux operator, because the flux operator is deployed inside pods, but it still schedules, but it kind of bypasses all of Kubernetes from inside pods rather than going out of pods to bypass Kubernetes. And how is kind of what interfaces of Kubernetes is it touching? So is it touching the scheduler? Is it touching one of the suspender gating fields? Or is it talking directly with Kube API? So I've kind of gone into a bit more detail about what each of these mean. So for what is being batched, kind of depending on what objects you're deploying, you get different things. So for example, pods have little to no guarantees about how reliable they are in their own right. Usually they're always controlled by higher level objects. Jobs are able to create multiple pods and ensure their behavior, so they can be more reliable. And then CRDs are extremely general and versatile objects. So it's pretty much impossible to predict in advance exactly what they're going to create with 100% guarantee. Where is being batched? So I've tried to give an explanation onto what each of these do. And then how it is being batched is just what I said before. So kind of Kubescheduler, suspend field, gating field, and then Kube API calls is just kind of my catch-all for anything else. And then from that, what you can kind of do is from a Kubernetes developer point of view, you can split all these solutions into 4 or so bullet points that give you a rough idea of how they're operating. So Q, for example, the what is jobs and CRDs, where single cluster for now, after the presentation 2 weeks ago. It uses the suspend field, and essentially this is the solution that gives you full utilization of Kubernetes. anything that's implemented in Kubernetes, you kind of get to take advantage of when you use Q. I think that's the biggest proponent of why to use it. Armada is pods and a multi-cluster, and it interfaces directly with the Kube API. And essentially, Armada does this because it means any of the throughput problems you'd have on Kubernetes, you can bypass. Essentially, it becomes a case of your program you can now schedule as quickly as, or accept into your queue as quickly as the program you write can on outside of Kubernetes. Flux operator is, as I talked about, like the idea of this non-batch object in the sense that it's doing scheduling from within pods themselves. And you kind of get the same benefits as you do with Armada. You don't deal with any of the throughput problems. You can scale beyond any kind of structures imposed by Kubernetes in theory. And you could also use a scheduler on top of the Flux operator. So you could have multiple levels of scheduling. And then I've got a couple other examples here, but you can kind of look through them in your own time. So in terms of coming away from this and thinking about what I kind of want to cover, I think this is a useful document to have. I think people sometimes miss what their solution is capable of, and what other solutions are capable of. And I think by having this document, we can better understand some of the reasonings behind decisions and why people might disagree on what your solution does and how it's implemented better through this framework. But yeah, I'm open to questions and any thoughts. Thanks.
Thanks a lot. Does anyone have any questions for Adam? One remark, I would probably share that broadly with the entire batch work group by sending an email to our mailing list. This would definitely have a little bit broader reach, and everyone is attending our calls. This way, you would be able to gather a little bit broader understanding of the document.
Oh, sounds good.
Okay, I think we have 10 minutes left. Francesco, do you want to present your demos, or people are okay closing today's call 9 minutes earlier?
Whatever folks prefer. I can.
Go ahead. We have 9 minutes.
Okay.
So it'll be recorded, and if
Okay.
anyone is,
So
they can always leave earlier.
sure thing. Okay. So gonna present a pre-recorded demo because aforementioned issues in getting a full multi-NUMA cluster. It's going to take roughly 3 minutes. Okay, now should be good enough. So we have this environment, which is a lab environment, which unfortunately I don't have access right now. So this is 2 worker nodes, 2 bare metal worker nodes with big machines, 2 NUMA nodes, and 50 and counting CPU per NUMA node. So those are the node resource objects I've described, which represent with the resource availability with per NUMA zone granularity. So you see we have roughly 50 CPU per NUMA zone and a bunch of memory and some fake devices. Because getting real devices was actually hard. The devices are just on 1 NUMA zone, not on 2 of them. And the 2 worker nodes are identical. This is the test set of pods. The The pods will need, of course, because we deploy the scheduler plugin as a secondary scheduler, you need to have an explicit scheduler name to leverage the NUMA-aware scheduling part. And we want to have guaranteed pods, which exclusive allocation of resources. So we are requesting 32 CPUs, a balance on memory, just to make, mostly to make them guaranteed quality of service, and devices. And because of the way we are requesting requirements on purpose, two of those pods cannot fit on the same NUMA zone. Now, yes, max 52 CPUs. Now 2 pods are 64, they cannot fit. Now we create them. This is a bit of noise. So we have 2 pods creating and 1 pod pending. And eventually they go running and this one stay pending. Why it stays pending? Because how the NUMA-aware scheduler plugin is working, because it's accounting resources properly, and there is no way you can fit this pod on the available zones. Because yes, you have 2 workers. Yes, those 2 workers, they have 2 NUMA zones, but the device which all pods are requiring are available only on 1 NUMA zone. So you actually have a maximum of 2 pods running, those 2 pods running, you know, 2 worker nodes, but only 1 NUMA node usable. So the third will hit the topology affinity error. Opting in, it will be rejected by the kubelet, will not admitted by the kubelet. So having opting in the topology we're scheduling, in the NUMA we're scheduling, means you prefer your pod to be pending instead of getting a huge stream of rejection from kubelets and having a bunch of pods which need to be cleaned up later. Now, so the 2 pods are hitting what different NUMA worker nodes for that very reason I explained. And this is actually behaving as expected, because we are now opting in, waiting for resources to be freed rather than getting continuous stream of rejection. Now we decide randomly to delete 2, could have been 1, could have been exactly the same. And when this happens, you will see that soon enough the pods, the pod 3 now should be go running, and those are the logs of the pod, the variables log of the pods, which will tell us when the pod is getting running. Because you see from the rapidly scrolling logs, you can see that the scheduler knows that it cannot align a pod, so it's waiting. But soon enough, it should pick up the changes from reported by the nodes, thanks to the agents running on the nodes, updates its state, learn that resources are now free, and then go and schedule, and the pod will go running. Takes some time for it to wake up. Okay, it happened. Now we do the counterproof. Exactly, this is now running. And the takeaway is that we didn't hit the topology affinity error because the kubelet, the scheduler managed to predict the behavior of the kubelet. So that was the demo I wanted to share.
Awesome. Thank you very much.
Thank you for listening.
And with that happy note, we are closing today's call. Thank you very much, folks, and see you again in